All right, so you guys on the website under chapter, this is unit 3, chapter 2, right here is review for test. Okay? All of these are answers to stuff. Okay, so this is the answers. If you're in Geometry 21, this is the A to Z proofs answer. Remember, this is a video explaining all of those proofs, but that's only for 21. This is just a whole bunch of random answers from random worksheets that we've done. So if there's something you're looking for the answer to and it's a worksheet we did a while ago, it might be in there. And then this is the Geometry 22 worksheet, review sheet that was given out in class most recently. And this is the Geometry 21 review worksheet that was given most recently. And then this is that basic geometry where you were given a given and then one conclusion from that given. We went over that in class mostly, but the answers are there. Okay? All right, so so in a little bit I'm going to go through what the test is going to cover for everybody. But just in the interest of time, I'm going to answer this person's question first. This is number 9 from the Geometry 21 review sheet. So this says, given BD bisects angle ABC. So as soon as you read your given, you can go to your diagram and mark it, right? So if BD is bisecting angle ABC, that means this angle ABC is getting cut into two congruent angles. So that's the first thing we're going to say, is angle ABD is congruent to angle DBC by definition of bisector. Then we could say their measures are equal by definition of congruent. Remember, anytime a statement goes from congruence to equals or equals to congruence, then it's definition of congruent. This, a lot of people got stuck here not knowing what to do next, but they never used the other given. So that's where you insert your other given. The other given is the measure of angle ABD plus the measure of angle C equals 90. That's just a given statement. So now from here to here, what happens? What happens from here to here? 90 stays the same. Angle C stays the same. Yeah, Emerson. Nope, and that's allowed because we already said they're equal. So you can knock that one out and replace it with DBC. That's substitution. And then since the measure of angle DBC and the measure of angle C equals 90, then we can say they're complementary by definition of complementary. That make sense? Okay, we had the question, couldn't number 5 also be transitive? And I just want to state again, right? Some of us talked about it in class, that sometimes substitution and transitive can be used for a certain step. Sometimes both are acceptable. But remember, with transitive, you have to have the second step has to link to the first step. In other words, one of the sides of the equation has to be the same for first step and second step. So if you look here, ABD equals DBC, and then this step, I don't have ABD on one side of this, or DBC on one side of this. You see what I'm saying? So it's substitution because there's no link that links them together. Like here, there's a link that links them together. There's no link here. And so checking for substitution, you want to find an equation that you're rewriting the exact equation. 90 and 90 stay. C and C. This is the one thing that swaps out. So it's an exact equation with one thing kicked out and the other thing put in. Okay, that's substitution. Okay, so for the test in general, chapter 2. All right, for all the classes. Okay, so in general, we're going to cover 2.2, 2.3, 2.5, and 2.6. Those are the things that are covered. 2.2, conditionals, if-then statements. So a conditional is just a statement, if something, then something else, right? If then. As part of learning about conditionals, we learned about the hypothesis and the conclusion. And the hypothesis was the part that follows the if. And the conclusion follows the then. In that section, we also talked about converses. And a converse is also an if-then statement with the hypothesis and conclusion switched. So, I am going to go to a new page and do an example of that. A square is a quadrilateral. I might ask you to write this as a conditional. How would you do it? Shakira. If it is a square, then it is a quadrilateral. And you may remember that I gave as a little hint in class, locate your verb. And your if part is what comes before the verb, and your then part is going to kind of be what comes after the verb. Okay, that's the conditional. What's the hypothesis? Just this blue writing here. That's the hypothesis. Don't include if in your hypothesis. What's the conclusion? Just it is a quadrilateral. So hypothesis, it is a square. Conclusion, it is a quadrilateral. What would the converse be? What would the converse be? Good. If it is a quadrilateral, oops, then it is a square. I just switched. Okay. Is this conditional true? If it is a square, then it is a quadrilateral? Is that a true conditional? Yes. Is the converse true? No. If the converse is false, or actually if any statement is false, you could come up with what we learned was called a counterexample. So since this is false, we could come up with a counterexample. What would a counterexample to this be? If it is a quadrilateral, then it is a square. Is false because, Gus? Yeah, a rectangle would be a quadrilateral that's not a square. Trapezoid, kite, any of those, right? Okay, so if it's false, you can come up with a counterexample. So let's just add that to what you need to know from section 2.2. Prove something is false. Okay. Then we talked about 2.3, which got into biconditionals. Okay, so in 2.3, we learned about biconditionals. And a biconditional is only going to be written when the original conditional is true and its converse is true. Also true, okay? And a biconditional is written like this. Hypothesis, if and only if, that's the key statement there, and then the conclusion. So whatever the hypothesis is, whatever the conclusion is, with if and only if in between. So you're not going to be able to write a biconditional for our example here because the converse was false. So you can't write the biconditional. So sometimes you're asked, state this as a conditional, identify the hypothesis, identify the conclusion, write it as a converse. Now decide, can you write a biconditional or can you give me a counterexample? It's really going to be one or the other. Yeah. So let's come up with an example. A right angle is an angle with measure equal to 90. So we could go through this same process. There's the verb. As a conditional, if it is a right angle, then it is an angle with measure equal to 90. I'm abbreviating here a little bit, but right? If it is a right angle, then it is an angle with measure equal to 90. So again, this would be your hypothesis. This would be your conclusion. If I write the converse, would it be true? Yes. The converse says if it is a measure with an angle with measure equal to 90, then it is a right angle, right? So if it is a measure, if it is an angle with measure equal to 90, then it is a right angle. We just switched the if with the then. Okay, turns out this is true and this is true. So we say, oh, okay, if it's both true, now I can write the biconditional. All right, so the biconditional, we just take the hypothesis. I wonder if this will let me. Oh, there we go. And then we take the conclusion. Oh, nice. And we just put if and only if in the middle. If and only if. So it is a right angle if and only if it is a angle with measure equal to 90 degrees. So you just take the hypothesis, take the conclusion, and you squeeze if and only if in between it. So the question was, does it matter which comes first? And it actually doesn't. I could have used this first. It is a measure equal to 90 if and only if it is a right angle. That works too. Okay? Since it's reversible, since it can go both ways, it doesn't really matter which hypothesis or which conclusion comes first. That make sense? Okay, then we talked about, oh, well, if that can be written, if you actually have a true conditional and its true converse, it can be written as a biconditional, then we have a good definition. because a good definition is reversible. So that's the criteria for a good definition. It's reversible. It can be written as a true biconditional. Original and converse are both true. So that is the other thing from section 2.3 that we needed to make sure we knew what makes a good definition. So it is a good definition that a right angle is an angle with a measure equal to 90. It's reversible. Works both ways, so that makes it a good definition. Okay. Okay, so 2.5 then, this is where we kind of broke it off and we started talking about proofs. Not that 2.2 and 2.3 don't have to do with proofs, because if-then statements are pretty much how we write every postulate and theorem. We usually write them as conditionals. So 2.5 started talking about all the properties. And we had addition property, subtraction property of equality, right? Division, multiplication, substitution, reflexive, symmetric, transitive. Let's add distributive over here. These three could be properties of equality or congruence. All of these are just properties of equality. We did a lot of algebra with that. Adding the same thing to both sides, subtracting the same thing from both sides. Okay? Remember, substitution property is when you take out one thing and replace it with something else into an equation. This is always in an equation, always. Can't be, nothing can substitute into anything except an equation. Then before we went into 2.6, I really sort of inserted a lesson in here. We had a worksheet called Practice for Proofs Chapter 2. And the whole front side had algebraic proofs on it. And then we walked through reminding ourselves of some of the definitions that are absolutely going to turn up in proofs. And so definition of, let's say, midpoint, bisect, perpendicular, complementary, supplementary, I guess right angle, linear pairs, vertical angles, what am I forgetting? Anything? Definition of congruent was one that we talked about, right? Definition of congruent. All of that gets used in proofs. And then we also talked about some of the postulates that we learned before. Linear pair postulate. Angle addition postulate. Segment addition postulate. All of those we use in proofs. Okay? And remember, the postulates are different from theorems because theorems have been proven to be true all the time, and postulates we accept as being true without proving them. Okay, so that's the difference between a postulate and a theorem. Okay, maybe we should talk about some of those for a second. Segment addition postulate. Remember, that's if one part of a segment plus the other part of the segment equals the whole segment. This part plus this part equals the whole thing. Whenever you're using that in a proof, it's never with numbers. It's always naming the segments. This little part plus that little part equals the whole thing. Okay. I could change this word to angle addition postulate, and it's the same idea. It's always going to be describing two angles adding up, actually 2 or 3 or 4 angles, right? Adding up to the whole angle. This angle plus this angle equals this whole angle. So you would say measure of angle A, B, C plus the measure of angle, what would I name next? Say again? Yep. Equals the measure of angle, yep, ABD. Make sure you recognize how to name those, right? A, B, C plus C, B, D equals ABD, the whole thing. Again, not with numbers or measurements, but just with naming the angles. And they're always going to be adjacent to each other because it's this little part plus that little part equals the whole thing. And then linear pair postulate we talked a lot about. Linear pair postulate, if two angles are linear paired, then they are supplementary. So it has to have that word supplementary in it. So when you're in a 2-column proof, if it says, here's these two angles, angle 1 and angle 2 are supplementary with the word supplementary, that reason is going to be the linear pair postulate. The postulate does not have the number 180 in it anywhere. So it would have to be the next step that says, okay, well then the measure of angle 1 plus the measure of angle 2 equals 180. What would be my reason here? Thomas? Nope. Definition of supplementary. Good. All right, that was one of our common triples. If you're in 21, we talked about common triples. Okay, so those are the postulates. Definitions you need to review on your own. Make sure you're remembering what those are. I've posted all the answers, so you should be able to figure those out. Remember, definition of congruent is used in a proof whether you're going from congruence to equal or equal to congruent. Either one, this is definition of congruent. Never going to be definition equal. Okay, 2.6 has 5 theorems in it. 5 theorems. Vertical angles theorem. Right? We talked about this already. If two angles are vertical angles, then they are congruent. So if you see this in a diagram, you could state angle 1 congruent to angle 3 by the vertical angles theorem. Right? The next one. Okay, so then we have right angles theorem, which says all right angles are congruent. So if you know two things are right angles, then you can say they're congruent to each other. Then we had the one that said, this doesn't have a name, if two angles are supplementary and congruent, then each angle is a what? Two angles are supplementary, meaning they add up to 180, and they're congruent, so they're both equal to each other, then each angle is a what? Right angle. Right? If they're equal to each other, they have to both be 90 to add up to 180. So is a right angle. Okay, then we had congruent complements theorem and congruent supplements theorem. And those both said if two angles are complementary to the same angle, so these two are both complementary to this one, then these two have to be congruent to each other. So if you know two angles are complementary to the same angle, you could say those two angles are congruent. And then congruent supplements theorem, same idea. If these two are both supplementary to the same angle, then these two have to be congruent to each other. Okay, so don't forget to check all your answers on your review packets and stuff. Don't forget that factoring is fair game on every test, okay? And for 21s, systems of equations is fair game on the tests, okay? Solving two equations at once, right? Solving a system like x and y, whatever. And that's it. Make sure you study all your notes and your worksheets. Okay, good luck.